Hello, I welcome you all to this another interesting screencast where we're going to be solving this engineering mechanics problem, and it reads determine the normal force, shear force and moment at point C. I'll say, and I'll also include this, draw the shear force diagram and the bending moment diagram. This problem is coming from the engineering mechanics statics textbook, 13th edition by Hibbeler. Right, to start with, we're going to draw the free body diagram. So we have simply supported, it's overhanging on both sides, and we have a couple at one end and a concentrated load at the other end. The support at A, we have a roller, therefore we expect a reaction force, which we're going to call AY. And at B, we're going to have BY, and another one we're going to call BX. Okay, so we're going to apply the equations of equilibrium so that we find these reaction forces. So we have summation of moments about point B equal to 0, and clockwise being our reference. So about point B, we expect a negative moment from the 10 kilonewton at lever arm 0.5, and then we expect another clockwise AY by R3, and then we have a plus 30, this couple, and it's equal to 0, right? Right, and therefore our AY is just going to be equal to, drop the calculator, minus 10 by 1.5 plus 30 divided by 3. So we have a 5 kilonewtons, right? Minus 10 by 1.5 plus 30, then divided by 3. Okay, then we're going to say again summation of forces in the Y equal to 0. Maybe let's move this down so that we have space. We bring it here. So summation of forces in the Y, like so, equal to 0. What do we have? We have AY plus BY minus 10 equal to 0. We've already calculated what AY is, so we are just going to replace AY there like this. And if we did so, therefore our BY is just going to be equal to, so that's 5 minus 10, 5 minus 10. Therefore our BY, we expect BY to be equal to 5. Okay, we expect BY to be equal to 5. Right, so we've calculated the support reactions. What we need to do now is we've remained with 1, right? So we have summation of forces in the x direction equal to 0. Of course we know this one, to say bx will just be equal to 0. So what we need to do now is we need to do the sectioning there, and let's do the sectioning. We have the left hand side, we have the left hand side and the right hand side. So I'll use the left hand side for no apparent reason. I've just chosen the left hand side. Okay, because they are all simple, of course. But if one side is much easier than the other, then go for the easier one that is not fully loaded. Okay, so we have a couple there, which is a 30, and then we have a support reaction there. So let's label this. We have AY. We said AY is 5 and BY is 5. So this is 5, and this is our C. So we expect our shear force like that, our moment like so, and our normal force like that. And this is all of them at a spacing of 1.5 meters and 1.5 meters. Okay, this point here is A. So let's apply the moments at C so that we find MC, then later on summation of forces in the Y. So summation of moments about point C equal to 0, and clockwise being our reference. What do we have? So we have a 30 anti-clockwise, and then we have minus as a 5 times 1.5, and then what else? Then plus MC equal to 0. Okay, therefore our MC is going to be equal to, so we have 30 minus 5 by 1.5. Alright, so this is a 22.5, so it's going to be negative. So minus 22.5 kilonewtons meter. So it's negative, it just means MC is supposed to be in the other direction. Okay, so let's move on to the other side. Let me also draw something there. Okay. Alright. So we have summation of forces in the Y equal to 0. Going up is our reference. What do we have? We have a 5 minus BC equal to 0. And therefore our VC is just going to be equal to 5 kilonewtons. And then we have summation of forces in the X, like so. So what do we have? The normal force is just going to be equal to 0 kilonewtons. So we found the moment MC. Okay, that minus just means the direction just has to change. Instead of it being anti-clockwise, it's going to be clockwise, right? For this particular section. All right. Then we have the shear force. Okay. Then we have the normal force. Right. So like I said, we are going to draw the shear force in the bending moment diagram. And we are just going to use the differential equations that relates the distributed load to the shear to the moment. So we know that the rate of change of moment with respect to x is equal to shear, and the rate of change of shear with respect to x is equal to the load. And of course, we also know that the areas under, we also know that moment, therefore, is just going to be equal to integral of the shear loading dx, or the area under the shear loading, and shear itself is equal to the area under the loading diagram. So we have moment, which is just area under the shear loading, and then the shear, which is just the area under the loading, the load diagram. So with these two equations, differential equations, we're going to use them to do the plots. Alright, so let's quickly do the plots. Let me draw just some quick lines there like so, and then I draw another one like so. Alright, so we have positive there, negative, positive, negative. So let's start the work. At the very end here, for shear will start at A. To start at A, so it will start at this point. Okay, we expect shear here to go up. Let me make this bold. Okay, so we'll have a shear value of 5. Let's say up to somewhere there. Shear value of 5. Okay, maybe this one is too high. Let me bring it up to there. Okay, so that I have some space. So we have a shear value of 5, and then between 5, or between A and B, we have no load. So we have no load. Okay, so this is what it means. So this is our shear force. Let me write down something there. This is our shear force diagram, and this is our bending moment diagram. Okay, so here we go. So I was saying our shear, our load between A and B, our load is equal to 0. Okay, and since we know that dV, or the rate of change of shear with respect to x, is equal to the load, and if the load is equal to 0 in the space that we are considering from A to B, we expect the slope also to be equal to 0, right? So this line here, okay, this point here has a magnitude of 5 kilonewtons. Okay, and then from there onwards to B, we are going to have a slope of 0, okay, up to By. When we reach By, we have another concentrated load, so these are going to interact algebraically depending on the sign. So when you look at the sign from A, it has a 5, positive 5, then at B it is also positive, so these are going to add, so it will be 5 plus 5, which gives us what? A 10. So it will rise by 5 like so. Okay, and then from B to the end there, again we don't have any loading in between, so the distributed loading is 0 between B and this end here. Okay, this end here, okay, just before 10, in between 5 and 10. And if that is the case, therefore expect again the slope of our shear diagram to be 0. So this just expect it to run like so. And then when it reaches where we have a 10 kilonewtons, again they are going to interact. This point here, we say it is a 10 kilonewtons, right? So we have a 10 positive, the other one is a negative. So when they add up, then this closes up, right? It will come down to 0, okay? And you expect this. When your diagram doesn't close up, then there's a problem. All right. So there we go. We have this shear diagram, which is all positive. All right. So now let's draw the moment diagram. So for the moment diagram, we use the same rules. We're going to use the same rules, and we know that for the moment is equal to the area under the shear diagram, right? But when we look at this beam, on one end of the beam, we have a couple that is applied. Okay. So we need to consider this. This is our initial boundary condition at the initial boundary condition. Okay. At this particular point, if you call this point, let's call it D. Okay. We have a load there that has been applied a moment. All right. So if you were to, and this moment here is negative. All right. This moment is negative. Okay. But if you were to make a section, just a very small section here, okay, we have this 30 kilonewtons. Realize that the internal moment that you are going to find there will be in the opposite direction, which is also a 30. Okay, and this one there, the internal moment, okay, is going to be a negative. It's a clockwise one. Okay, and that is the one that we are going to use when doing the plot. All right. So negative is down. Let's say our 30 is down here. Our 30, let's say it is somewhere here. It starts somewhere there like so. This is our 30. And then between this couple moment, okay, and A, we don't have any shear force. Let me see. The shear force, shear between D and A is 0. So shear is equal to 0. We don't have any shear, okay, and therefore the slope for the moment, okay, is also going to be equal to 0. Okay, so it's just going to be 0. So we just expect a straight line for moment from 30. This point here is 30. This point here is 30 kilonewton meters. So you expect just a constant value. You just expect a constant value, right? Just expect a constant value from there to here like this. Okay. But when you reach at this point A there, okay, this region has some shear, okay, and the shear there in this region is positive. Shear is positive, and it has a constant value. So shear there is equal to is positive 5. Okay, it's positive 5. All right, and it is constant. Okay, it is constant throughout, right? And therefore our slope of the moment is also going to be equal to 5. So it will have a positive constant slope. All right. So we need to calculate that value, what value it is. And we know that the area under the shear diagram or shear loading, it gives us the moment. So we'll do it in parts. So from A to B, we have a 5 times 3, okay, which gives us 15. Okay, so we have a 15 from A to B, but mind you, we have a 30 there, okay, and this 30 is negative, then the other one is positive, so we'll have minus 30 plus 15. What does this give us? This gives us a minus 15. Okay, So we expect this from this end here to move with a with a positive slope, constant positive slope, up to a value of minus 15, somewhere there like this. Let's say up to we can assume that one is our 15, like so. All right. So what is this value here? This value here is, we say this is a 15 because we have negatives here. This is a 15, it's negative, it's still negative. Okay, and then this other region here, we need again to compute the area. The slope will still be positive. So the area there is equal to a 10 times the length, which is 1.5. So this gives us a 15. But where we are coming from, we have this initial value, which is 15. So it's a minus 15 where we're coming from, then plus the new value that we just calculated, which gives us a 0. So therefore, from that end, this is going to close up. We're going to move from this point. We'll move from this point. This point is supposed to be directly with this line, like so here. Okay. Supposed to be in line with that nicely. Okay, something like that. Right. So we have that one as our 15. So we said, then we have, yeah, something like that. So we said when they algebraically sum up, then we expect this to close up like that. Okay, with a positive slope. Okay, with a positive slope of 10. All right. So this is a negative moment. This is negative, and this is positive shear. All right, I think this is about it. Let me just get rid of this. This is about it. So we have drawn the shear force diagram. Let's check out what we've done here. See, it is somewhere here. C for shear, we found a 5, yes, positive. And then for moment at C, okay, this point also is 30. This is also 30 here. Kilonewtons, this is kilonewton meter. So between 30 and 15, we found a 22.5, which is a negative, right? Which is a negative. Okay. And for sure, this is the moment that is in between 30 and 15. Okay. Yes, that's a 22.5. So everything else is fine, and I hope the video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.